Welcome, space enthusiasts and curious minds. Today, we're diving into a groundbreaking revelation from the James Webb Space Telescope that's sending shockwaves through the scientific community. It's about the Big Bang Theory, the cornerstone of our understanding of the universe's origins. But what happens when the most advanced space telescope tells us there's something we might have gotten wrong? Let's explore this cosmic conundrum and unravel the mysteries of the universe together. At the dawn of the 21st century, cosmologists appeared to be on the verge of unlocking the ultimate mystery, the workings of the universe. Their toolkit for this monumental task included a variety of methods, charting galaxies and their vast networks, observing the dramatic explosions of stars known as supernovae, gauging distances to stars whose brightness varies, and analyzing the ancient cosmic microwave background radiation that permeates the universe. These different approaches to studying the cosmos began to converge, suggesting that the pieces of the cosmic puzzle were fitting together. The pivotal moment in this convergence came in 1998 with the discovery of dark energy. This enigmatic force, far from acting as a cosmic adhesive, was found to be driving the universe to expand at an accelerating rate, defying the expectation that the expansion would slow over time. With the incorporation of dark energy into their calculations, scientists found that the theoretical framework and empirical data began to align more closely. This led to the formulation of what is known as the lambda cold dark matter (CDM) model, the standard model of cosmology. According to the CDM model, dark energy constitutes nearly 70% of the universe's total content, dominating the cosmic landscape. Another elusive component, known as dark matter, accounts for about 25%. This invisible substance appears to interact with the visible matter primarily through gravitational forces. The rest, a mere 5%, comprises all the matter and energy that we can directly observe. This model represents a significant milestone in our understanding of the universe, encapsulating our best explanations for its structure and evolution. Gazing at the stars, planets, and galaxies has been a source of awe for astronomers over the millennia, offering moments of tranquility amidst periods of intense challenge. As the precision of astronomical observations increased through the ages, especially with the advent of cutting-edge telescopes like the James Webb Space Telescope, significant cracks began to show in the standard cosmological model. Early indications of these discrepancies arose from the study of variable stars and supernovae within a few nearby galaxies. When these observations were compared to the ancient cosmic microwave background radiation, it suggested that the universe might operate under different principles than previously believed. Specifically, a key cosmological parameter, which dictates the rate at which the universe is expanding, appeared to vary depending on the method used to measure it. This inconsistency presented cosmologists with a significant quandary, at times referred to as a tension, or more dramatically, as a crisis. In the decade following the initial observations, these discordant measurements have grown only more pronounced, highlighting not just one, but multiple challenges to the standard model of cosmology. For instance, observations of how galaxies and cosmic structures have aggregated over time hint at a discrepancy with predictions based on our understanding of the universe's evolution from its early stages. This ongoing debate suggests that our current models may need revising to fully comprehend the universe's mysteries. Subtler discrepancies have emerged from intricate analyses of the universe's primordial light, among other inconsistencies. Eleonora Di Valentino, a theoretical cosmologist at the University of Sheffield, observes that the scientific community is facing numerous minor issues alongside the major ones, adding layers to the puzzle. To address these discrepancies, cosmologists are employing dual strategies, refining their observations of the cosmos in hopes that improved data will offer new insights, and adjusting the standard model in attempts to account for these unforeseen findings. However, these adjustments often feel forced and may resolve one issue only to exacerbate another. Presently, our understanding of cosmology appears muddled, leaving experts uncertain about the direction forward. Scientists describe the universe using a set of key numbers known as parameters, which are akin to cogs in a vast cosmic machinery, each interconnected. Among these parameters, the Hubble constant, which measures the current rate of the universe's expansion, has been a subject of contention for over a decade. This situation underscores the complexity of the universe and the challenges faced in constructing a coherent model of its dynamics. The initial signs of discord in cosmological measurements, specifically concerning the current rate of the universe's expansion, emerged subtly. It required several years of data collection for the majority of cosmologists to acknowledge that this discrepancy represented a significant crisis. The core of the issue lies in the mismatch between the expansion rate measured directly in the contemporary universe and the rate predicted by extrapolating from conditions in the early universe, leading to what is now termed the Hubble tension. To determine the Hubble constant, which quantifies this rate of expansion, astronomers need accurate distance measurements within the local universe. For this purpose, they rely on a type of star known as a Cepheid variable. These stars exhibit periodic variations in brightness, with a direct correlation between their pulsation period and luminosity. This relationship, uncovered in the early 20th century, enables astronomers to deduce a star's true brightness from its observed brightness, thereby estimating its distance. Using Cepheid variables, scientists can measure distances to galaxies up to approximately 100 million light-years away. For observations extending further into both greater distances and deeper into the past, astronomers employ even more luminous markers. A crucial tool for measuring cosmic distances is a particular type of stellar explosion known as a type Ia supernova. These events serve as standard candles because their intrinsic brightness can be accurately determined, enabling astronomers to measure distances to galaxies billions of light-years away. Over the last 2 decades, such measurements have allowed astronomers to estimate the rate at which the nearby universe is expanding to be approximately 73 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, you look farther out into space. Galaxies are moving away from us 73 kilometers per second faster. However, this rate significantly contradicts the rate calculated from observations of the early universe. In the universe's infancy, it was a dense, hot plasma of fundamental particles and energy, described by cosmologist Vivian Pollin of the University of Montpellier as a hot mess. A fraction of a second after the Big Bang, an event possibly related to a period of rapid expansion known as inflation, sent shockwaves through this primordial plasma. As the universe expanded and cooled, the light that had been trapped within this plasma was finally released. This light, known as the cosmic microwave background, CMB, provides another method for measuring the universe's expansion rate, but it yields a different value from that obtained by observing type Ia supernovae, leading to the current discrepancy known as the Hubble tension. The cosmic microwave background, CMB, captures the remnants of the early universe's pressure waves, akin to how the surface of a frozen lake preserves the crests of waves in a moment of stasis. By analyzing the predominant wavelength of these preserved waves, cosmologists have deduced a value for the Hubble constant, approximately 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. This figure starkly contrasts with the roughly 73 kilometers per second per megaparsec estimated from supernova observations, fueling an intense debate within the field of cosmology that remains unresolved. The James Webb Space Telescope, JWST, with its unparalleled infrared capabilities, large mirror, and advanced optics, has further entrenched this debate by providing new measurements that underscore the discrepancy. JWST's ability to distinctly capture the light from individual stars without the interference of neighboring stars has been instrumental in this endeavor. In its first year, under the General Observers Program 1685, JWST collected data on Cepheid variables previously identified by the Hubble Space Telescope. This involved the observation of Cepheids in a galaxy whose distance had been geometrically determined, allowing for the precise calibration of Cepheid's true luminosity, a critical step in the cosmic distance ladder. In our study, the galaxy NGC 4258 serves as the starting point. The subsequent phase involves examining Cepheids within the galaxies hosting type Ia supernovae. This two-step process enables the calibration of the supernovae's intrinsic brightness by establishing the distance to these cosmic beacons. The third step entails observing these supernovae in distant galaxies, where the universe's expansion is observable. By comparing the distances derived from the supernovae's brightness with the redshifts of their host galaxies, scientists can measure the expansion rate. This method, known as the distance ladder, has recently been advanced with the first data from the James Webb Space Telescope, JWST, covering the initial two steps, thereby enhancing our ability to construct the distance ladder and compare it against prior Hubble Space Telescope measurements. Thanks to JWST's superior resolution in the near-infrared spectrum, the precision in Cepheid variable measurements has significantly improved, reducing the uncertainty that previously existed. This improvement is exactly what astronomers have long hoped for. JWST's observations of over 320 Cepheids in these initial phases have essentially verified that the discrepancies noted by the Hubble were not anomalies but indicative of a genuine need to refine our calculation of the Hubble constant in the present-day universe. Navigating beyond the expertise of even the most seasoned astrophysicists, the issue might involve dark energy, dark matter, or the nature of gravity itself. There's a possibility that our interpretation of the data is accurate, yet our understanding of Cepheid variables' fundamental properties could be flawed. As it stands, the mystery remains unsolved. James Webb Space Telescope's examination of the Hubble constant underscores the reality that there's much more we need to uncover. Cosmologist Adam Rees of Johns Hopkins University describes this situation as a significant anomaly or surprise that has left the scientific community in a state of confusion, akin to a purgatory. It suggests a flaw within the standard model of cosmology, yet there's uncertainty about how to adjust it, in what direction, or by what means. However, this challenge over the Hubble tension shouldn't be viewed as a cause for despair, but rather as an exciting opportunity to deepen our understanding of the cosmos. As the James Webb Space Telescope continues to refine our knowledge of critical cosmological parameters, scientists are diligently working to align this new data with their existing models of the universe. The hope is that more precise measurements might resolve these discrepancies, or it could turn out that these tensions are merely the result of something more prosaic, such as peculiarities in the observational instruments used. The discrepancies might indicate that our current models are insufficient and that breakthroughs in new physics are necessary. J. Colin Hill, a theoretical cosmologist at Columbia University, highlights this crossroads, suggesting that either our existing models lack the sophistication needed to encompass all phenomena, or we're on the cusp of discovering multiple new physics aspects. These could include a previously unidentified fundamental force, novel interactions among dark matter particles that remain unexplored, or entirely new components not yet incorporated into our cosmic framework. Some innovative theories propose modifications to dark energy, suggesting an initial burst of cosmic acceleration that occurred just before electrons and protons combined. Mark Kamionkowski, a cosmologist at Johns Hopkins University, posits that a slight temporary increase in the expansion rate during the universe's nascent stages could potentially reconcile the Hubble tension. This hypothesis, which Kamionkowski and a doctoral student introduced in 2016, also predicted specific markers that a high-resolution cosmic microwave background telescope could detect. The Atacama Cosmology Telescope, situated in the Chilean mountains, has indeed observed some of these anticipated signals, adding an intriguing layer to the ongoing investigation. Other researchers have identified that such models, which introduce a temporary surge in a new type of dark energy, clash with existing cosmic observations. Dragan Huterer, a theoretical cosmologist at the University of Michigan, has critiqued these finely calibrated models for their complexity, suggesting they do not convincingly resolve the observed phenomena. Additionally, other suggested solutions to the Hubble tension often align even less with empirical data, appearing overly tailored and reminiscent of just-so stories that failed to conform to the scientific preference for simpler, more elegant theories. Upcoming data releases could provide further clarity. The first set of insights will come from the team led by Friedman, examining various measures of the nearby universe's expansion rate. Following that, in April, the first results from the most extensive cosmological sky survey to date, conducted by the Dark Energy Spectroscopic Instrument, will be unveiled. Later in the year, the Atacama Cosmology Telescope team, along with researchers using the South Pole Telescope to create another map of the primordial background, are expected to publish their high-resolution findings of the cosmic microwave background. Further insights are anticipated from the European Space Agency's Euclid Space Telescope, promising observations from even more distant reaches of the cosmos. Launched in July, the Vera Rubin Observatory is another groundbreaking venture, an all-sky survey project currently under construction in Chile, expected to be fully operational by 2025. While the universe may be 13.8 billion years old, our journey to comprehend its vastness and our place within it is just beginning. The seeming harmony within cosmology that existed merely 15 years ago has since dissolved, revealing that what appeared to be a period of calm was, in fact, a prelude to a series of discoveries that would challenge long-standing theories. The fissures that emerged a decade ago have since widened, casting doubt on the once favored models of the cosmos. In a recent revelation, a stunning new image from the James Webb Space Telescope showcases a vast star-forming region in a neighboring galaxy with remarkable clarity and in vibrant hues of orange, yellow, and blue. This image captures the interstellar atomic hydrogen of the 13 light-year-wide Nebula N79, situated in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This area, actively engaged in star formation, has largely remained uncharted by astronomers. N79 is viewed as a nascent counterpart to the Tarantula Nebula, another subject of recent James Webb observations in the Large Magellanic Cloud, located about 161,000 light-years from Earth. Despite their differences, these celestial phenomena share intriguing similarities. Researchers believe that for the past 500,000 years, the Nebula N79 has been generating stars at a rate double that of the Tarantula Nebula, also known as 30 Doradus. By examining areas of vigorous star formation like N79 through the lens of the James Webb Space Telescope, scientists gain insights into the makeup of the gas and dust clouds where stars are born, particularly relevant to understanding the conditions prevalent in the early universe when star formation was at its peak. The recent imagery from James Webb highlights three vast regions of cold atomic gas, known as molecular clouds, which together form an area referred to by astronomers as N79 South Orson. A notable feature of this image is the radiant starburst pattern that emanates from N79's luminous core, a result of diffraction spikes created by the telescope's 18 hexagonally arranged mirror segments, resembling a honeycomb structure. These 6 primary diffraction spikes occur when James Webb observes especially luminous and concentrated celestial bodies, with light emanating from a focused point. As the $10 billion telescope trains its gaze on galaxies, even those that might seem minuscule, the light it captures is more dispersed, leading to a diffraction pattern that reflects the more spread-out nature of these cosmic light sources. The James Webb Space Telescope captured the remarkable image of N79 utilizing its mid-infrared instrument, MIRI. While dense clouds of dust readily absorb visible light, they are more permeable to long-wave infrared light, allowing MIRI's infrared capabilities to unveil the hidden depths of this star-forming region. This technological advantage enables James Webb to detect young stellar objects still enveloped in their birth clouds of gas and dust. These protostars have not yet accreted sufficient mass to initiate hydrogen fusion into helium in their cores, the process which ultimately defines a star. Among the celestial spectacle, an infant star beginning this fusion process shines brightly, set against a backdrop of swirling orange gas and dust clouds in the N79 image by James Webb. The telescope's investigation into N79 contributes to its broader mission to explore the evolution of disks and envelopes of material that encircle stars at various stages of their life cycle. Through this mission, James Webb aims to provide astronomers with unprecedented views of planet-forming disks around young stars akin to our Sun, offering insights into the genesis of our own solar system. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.